I am Karma Tinsel. I am here with my project titled Earthquake and Rainfall App, and this project is guided by Mr. Tanimachu. Overview. So these are some of the outlines I'll be discussing in this presentation. Let me begin with a very brief background. P-Alert is a seismic sensor. It is an advanced earthquake P-wave alarm designed and developed by Sandian Technology Corporation in Taiwan. In several countries like Taiwan, New Zealand, Indonesia, and US, the use of the P-wave-based P-Alert system provides timely and accurate information and provides answers on earthquake warning-related questions. The specially designed and scientifically proven algorithm make the P-Alert unique in pre-warning. The College of Science and Technology, with assistance from the IAS-PEI, has established 12 stations installed with P-Alert sensors and systems to capture seismic and rainfall data. These stations are scattered in parts of Phuntsholling and Gedu, forming a regional network. So the problem statement: first, base stations capture data and send them to the server, where it remains unexploited when they can be a valuable asset to use. Secondly, public or any personnel has no convenient means of access to this data, nor there is a pertinent platform or a proper platform or a system to utilize this data. With the problem statement identified, the project was designed to carry out efficient disaster response with a mobile app to increase awareness and guide public attention to mitigation actions with information dissemination. To be able to achieve the aim of the project, some of the objectives identified were importing the earthquake and rainfall data to the mobile app, implementing data visualization on earthquake and rainfall data and display it on the mobile app, and to enable push notification on the mobile app for earthquake event as an early warning. The scope of the project encompassed the development of app for monitoring and visualizing the data in the server. Any predictive or data analysis were not carried out in this project. Now the concept of the early earthquake warning. Seismic waves are generally categorized as primary P waves and secondary S waves. The primary P waves are known to travel twice the speed of secondary waves and are less destructive. However, S waves are slower and can be highly destructive. For example, if it takes P waves about 20 seconds to reach location L2 from L1, then the S waves will follow in the next 20 seconds after the P waves has arrived at location L2. So this nature of the seismic waves enable the P-Alert seismic sensors to detect P waves earlier than S waves and provide an early earthquake warning. So it is just like how we can see lightning before we can hear the thunder. The amount of the advanced warning solely depends upon the distance from the point of rupture or the epicenter. So this figure demonstrates how the P waves travel faster than S waves. This nature of the P waves to travel faster than S waves enable the P-Alert sensors to send signals to the server from where the early earthquake warning can be deployed to places where the S wave is going to hit. So the idea here is when a station intercepts P waves, it transmits a signal back to the server. The server instantly deploys early earthquake warning in the form of notification in all the places where P waves has arrived and S waves are yet to arrive. The project boundary, to distinguish the scope of the project from the existing system, all the components on the left-hand side of the line were not built or developed in this project. These components or systems are already prevailing. For example, the sensors at the base station and the dedicated server for data storage were already existing. So this project was basically built on top of this existing infrastructure. So all the components on the right, however, which includes the backend program, FCM configuration, from push notification, API, and mobile app, are part and work breakdown for this project. Now let me discuss the system architecture one by one. First, the backend program. This program has two parts to it. First is the data migration program. The P-wave signals intercepted at the base stations are realized as files in the server. The existing system captures both the seismic and rain data in the form of flat files. So the data migration programs, what it does, it migrates the data from file storage to a dedicated database. The data migration is further two-part. First is the watchdog program. The watchdog program monitors certain folder or directory for any create, read, update, or delete operation on it. The second part is the migration program itself. So when the new data are added to the server, Watchdog program senses the change, and then the migration program migrates all the data into the database from the newly added file. The next part of the backend program is the program to trigger the broadcast alert. When P waves are detected at the base station, seismic data file is dumped at the server. The Watchdog program detects the new seismic file and then tells the trigger program to broadcast the message to the notification server, which is the FCM server. So this is the screenshot of how the Watchdog program detects a file created event and how it sends out broadcast message to the notification server. Now the database. A database is employed for data storage for all the data storage of all the migrated data from the flat files. PostgreSQL is a relational database and it is used for data storage in this project. Notification server. For the purpose of notification, push notification, FCM, which is Firebase Cloud Messaging, was employed. The API, REST API, for the communication between the app and the early earthquake warning server, REST API is employed, which in turn produces a JSON response of earthquake and rain data. So this figure is a sample of the JSON response for earthquake data for station 1. Please note here that there are many data points for an earthquake data. So similarly, this figure is a sample of the JSON response for rain data for the January month of the fiscal year 2020. So now app at the user end. Users can use the app to view the earthquake data and rain data, and most importantly, it can be used to receive timely early earthquake warning before the arrival of the S waves in case P waves are detected at the base station. Now, the push notification as early earthquake warning. Now, I'd like to provide a very comprehensive explanation of how the notification or the push notification is employed to achieve the early earthquake warning. So we'll start from left. When P waves are detected at base station, the backend server sends out a broadcast alert to the FCM server. The FCM server, in response to the broadcast alert, rolls out push notification as an early earthquake warning to all the registered users. So for this purpose, users have to subscribe to the FCM server so that they are identified by the FCM server during the rollout. In order to register, there is a registration feature in the app, and a demo for the registration will be seen in the demo section. Now let me explain now let me go through the app demo. So basically, I have the app. The app has been named as eQuick. So we can see here the eQuick app. So upon opening the eQuick, we have the splash screen for a moment, and then the home screen for the app. Before I go on explaining with the screens of the app, I'd like to discuss demonstrate the side drawer for the app. So in the side drawer, I have 5 components: registration for notification button, then 4 menus, which is the earthquake, rainfall, safety tips, and the setting. So under the earthquake menu, we have station as submenu, where we can view the data for all the stations and their seismic data. And similarly for the rainfall, submenu, we have months as the submenu, where we can view the rain data on the basis of month. Now let us look at the earthquake data. So for a particular station, we can view the seismic data as recent and past data. So in the recent, we can view the most recent data recorded or intercepted at a particular station, while in the past data, we can view the seismic data, which is second to the latest seismic data recorded for that particular station. So this we can see the graph here. This graph is a combination of 3 different data, which are nothing but the accelerations of the sensors, acceleration of the sensors at the base station. So this is composition of 3 different lines. We will see that a bit later. So the rainfall data, like I said, can be viewed on the basis of month for all the stations. So this in the recent, like we saw in the earthquake, for the earthquake data, we have recent and the past data. So in the recent data, we can view the monthly rainfall for the particular, for the current year. And for the past year, we can view the monthly rainfall for the previous year for particular month. So here we have a black line that runs through the graph. This is nothing but the line of base width. We can, in case we don't want to see the line of base width, we can simply deselect the line which we see on the linear label on the bottom of the screen. We can also simply, we can also tap on the bar to view the individual data, like this. So we can view the individual data by tapping on the each bar. So we have this aspect. Now let us look at the earthquake data. Like I said, the earthquake data is a composition of 3 different data types. We can view the individual graph by simply deselecting labels on the bottom of the screen. So this is the accelerations for acceleration values for different for the different dimensions. So the blue represents the acceleration in x-axis, the brown represents for the acceleration in y-axis, and the red or the pink represents the acceleration in z-axis. So in the safety tips menu, we have the instructions for the users as to how to prepare, survive, and to recover during the.
You got 3 minutes.
Thank you, ma'am. And these informations are directly extracted from the Department of Disaster Management of Bhutan. So in the setting menu, we have the aspect to turn on and off the notification. So this is the demo for the app. Now let us look at the registration app, a registration demo. So like I said, for the users to receive FCM notification as an early warning, users have to register themselves with a valid email address. So they have to provide valid email address. So before registering, let us ensure that there are no mails prior to the registration from the server. So there is no mail. Now, after hitting the submit button, we get a toast message saying the device has been registration, and the screen is redirected to the home screen. So if we go back and check our mailbox, we receive a notification from the server, which puts content, if we on viewing, says that the device has been successfully registered. So this is the demo for the registration. So we use a valid email address here. So this is how the user's information are stored in the database in the server. So now let us look at the notification demo in the application. So I took about 4 devices together and then tested notification. So when P waves are intercepted, the early earthquake warning is received as a notification at the user end, as demonstrated here. So the notification delay or the lag between among the devices are quite less significant. So the notification delivery is quite same. So this is the notification demo. Now let us look at the EQ timer demo that we missed out earlier. So the users, upon receiving the early earthquake warning as notification, they can simply use the EQ timer to keep track of the time left before the arrival of the S waves. So when this countdown hits the 0, it is likely that the user will experience a secondary wave or the earthquake, or basically the earthquake. So users can make use of this EQ timer and keep track of the time for evacuation. So this is the significance of the EQ timer. So this brings to an end of my presentation. Thank you for your kind attention.